Good morning, everyone. Myself is Kiran Mahi, the Assistant Professor in Physics from Government City College. Today, now we are discussing with the low temperature physics. Low temperature physics is nothing but a first order phase change is one which is accompanied by the emission or absorption of heat without any change in temperature. For example, consider the first order phase transition in a given mass of water. When water is heated at constant pressure, the temperature increases uniformly and heat absorbed increases the internal energy of water. At boiling point 100 degrees Celsius, the internal energy absorbed changes the phase of water into gaseous phase. That is where the temperature remains constant. The amount of energy supplied to convert water into steam at the boiling point is called specific latent heat of vaporization. Similarly, when a given mass of water is cooled, its internal energy decreases uniformly till freezing point, that is nothing but 0 degrees Celsius. Now, this will gives you the specific latent heat of fusion. Now, that is nothing but when water is converted into solid phase called ice. Now we are going to see the important picture of Joule Thompson or Joule Kelvin effect. Joule Thompson effect is nothing but the principle is nothing but when PQ is a thermally insulated cylinder containing porous plug. Porous plug is nothing but a material which is like cotton or wool, okay, and is fitted with the two non-conducting pistons, capital A and capital B. The porous plug separates the cylinder into two parts. The gas is compressed to a high pressure P1 on one side. The gas then passes through the porous plug on the other side. There is a constant lower pressure on P2 side. When the compressed gas molecules come towards the lower pressure side after passing through porous plug, they are drawn apart and hence suffer a change in temperature. The change in temperature is called as Joule Thompson effect. This effect is stated as when a gas under a constant pressure is passed through a porous plug to a region of lower constant pressure, the gas suffers a change in temperature. Such a change was actually demonstrated by Joule Thompson. Hence, this experiment is also called as Joule Thompson effect. Now, what are the results of this Joule Thompson effect? The results are nothing but when all the gases suffer a change in temperature after passing through the porous plug. At ordinary temperatures, all gases except hydrogen and helium show cooling effect. For example, at 0 degrees Celsius, hydrogen shows a heating of 0.04 degrees Celsius for atmospheric pressure difference. The change in temperature is directly proportional to the difference in pressure on the two sides of porous plug. The fall in temperature for atmospheric difference of pressure decreases as the initial temperature of the gas is raised. It becomes 0 at a particular temperature, which is different for different gases. Above this temperature, instead of cooling, heating is observed. This particular temperature at which Joule Thompson effect changes, the sign is called as temperature of inversion. Thus, every gas below its temperature of inversion will cool on passing through the porous plug. The inversion temperature of hydrogen is minus 80 degrees Celsius. So if it is pre-cooled to a temperature less than -80 degrees Celsius, then passed through the porous plug, it suffers cooling. Now we will see how this gas will be passes from one chamber to the other chamber. Now suppose that the piston A is moving towards the porous plug. The result is that a mass of gas is transferred from left compartment to right compartment. Here it is assumed that the high pressure is left compartment and low pressure is on the right compartment are kept constant. Because the compartments are thermally insulated, the piston is moved very slowly. Let P1, P1, T1 represent pressure, volume and temperature on high pressure side, and T2, V2, T2 similarly quantities on low pressure side. Let U1 and capital U1 and capital U2 be the internal energies of unit mass of gas before and after passing through the porous plug. Therefore, work done on the gas by piston A is P1 V1 and work done by the gas on the piston B is P2 V2. Therefore, that is nothing but A equals to P1 V1, B equals to P2 V2. Therefore, the work done is nothing but P2 V2 minus P1 V1. P1 V1. As the system is thermally isolated, this work must have been done at the expense of internal energy of the gas. Hence, this will be equals to your internal energy U1 minus U2. That is nothing but U1 plus P1 V1 equals to, this is nothing, this will be equals to your internal energy. Internal energy, that is P2 V2 minus P1 V1 equals to U1 minus U2. This implies U1 plus P1 V1 equals to U2 plus P2 V2. This is nothing but a constant. Now we have got a Joule Thompson effect. The quantity U plus PV is nothing but enthalpy. Thus, in Joule Thompson effect, the initial and final enthalpies are equal. That is nothing but for a perfect gas. In case of perfect gas, Boyle's law is obeyed. That is nothing but P1 V1 equals to P2 V2. Hence, U1 equals to U2. Now, the Joule Thompson effect is zero for perfect gas. That is nothing but P1 V1 is not equals to for P2 V2 for real gases. Below the boiling temperature, experiment shows the P2 V2 is greater than P1 V1. At boiling temperature, P2 V2 equals to P1 V1. Above boiling temperature, P1 V1 is greater than P2 V2. Thus, the internal energy of the gas will increase and hence temperature will rise. Now, this is the importance of the Joule Thompson effect. Thank you.